All right, guys, today we're going to start talking about graphing motion. I know you should have worked on an outline for it last week, so you should be a little bit familiar, but we're going to start from scratch. To start off, I want you guys to watch this little video.
A graph gives us another way to describe an event. This graph of distance versus time tells the story of a girl named Chris and her dog during an 8-minute walk. As Chris and her dog move farther from home, the graph line moves upward. When they stop, their distance from home is not changing. The graph line moves upward again as Chris and her dog start walking again. The graph becomes horizontal, telling us that they have stopped again. Chris and her dog have now turned toward home. The steepness of the graph tells us that they are moving faster, probably running. At the end of the walk, 8 minutes have passed, and the distance from home is again 0.
So today we're going to be looking at how to use graphs to describe motion. And to figure that out, I'm going to start by drawing you a few graphs. So this first one is called a position time graph. Now, I should remember from last week that we mark time with the variable t for time, and position, which is where you are, we call x. X equals position. Now, graphing in physics is a little bit weird, especially for people that have never done it before, because you're really used to an x and y coordinate system. That's what is used in math. But in physics, we can have anything we want on the axes. We get to choose what variables we're using. And right now, for a position time graph, position versus time, we need to use time and position. Now, time is the thing we can't control. It's the independent variable, and the independent variable always goes on the horizontal axis. So we're going to put time down there on horizontal, which leaves position, or x, on the vertical, which is not where it normally is in math, so it's going to take a little bit of getting used to. So I'm going to draw a graph and we're going to talk about what it is. The first graph is just a horizontal line like that. So we're going to think about a person who would be following the line of this graph. So at time equals 0, because right here at the beginning is 0, time equals 0. They're at some position x. For argument's sake, we'll just call it 3. They're standing at some place that we're going to call 3. And as time passes, we're going to go a little bit at a time. As time passes, they don't move from position 3. They're always at 3 on that position axis. So they're not moving at all, which means their velocity or their speed equals 0. So anytime you have a horizontal line, your position isn't changing. You're staying at the same x, staying in the same spot the whole way across. That means you're not moving, which means your velocity is 0. So what you need to remember is that horizontal or flat means that your velocity is 0, that you're not moving. Now let's look at another one. Let's look at one where we start down here and we go straight up. Awesome. So what we notice, or what's happening in this picture, is we start somewhere. We start at time 0 and at position 0. And as time increases, going that way, as time increases, so does x. This means that the object we're looking at is moving steadily forward as time progresses. And when the line is straight like this, it doesn't curve. Whenever it's straight, that's called a constant velocity. Constant velocity. Constant velocity means that their speed doesn't change. Speed doesn't change. But one thing that is important about velocity is direction. It's what we call a vector. And a vector is a number and a direction. So when we're talking about the velocity in regards to a position time graph, we have to know which direction the object is moving. And in this graph, it's moving in a positive direction because, you know, up is positive and down is negative. However, if our graph looked like this with a straight line, assume I can draw a straight line that's supposed to be a straight line, but it's headed downwards, that means we have a constant velocity in the negative direction because down is negative. So real quickly, we're going to look at a thing called slope on a position time graph. This is position versus time. We're going to make the middle the time axis right there, and we're going to make the x-axis over here with negative x, positive x. Time is going to be in seconds. X is going to be in meters. So say, for example, I start at 0, and as time progresses, I move along to this point over at 1, 2, 3, 4, 5, 6, 7, 8, 9 seconds. Let's make it an even 10. So at 10 seconds, I'm going to be right there. Get rid of that dot so it's not confusing. Okay, so at 10 seconds, I have moved all the way from 0 up to x equals 2. Got 1, 2. So we're going to think about how far I went and how long it took me to get there. If I started at 0 and I went to 2 meters, that means I traveled a total distance of 2 meters, which we write as change in x, because that's how much my x changed. Change in x equaled 2. And it took me 10 seconds, so my change in time equals 10. Now, we should have been learning about a nice equation called the velocity equation, which says velocity equals delta x divided by delta t. So what I can do is I can take these two numbers that I just read off of my graph, plug them into this formula, and find my velocity. So when I do that, I get velocity equals 2, because delta x equals 2 over 10, because delta t equaled 10. And that, 2 divided by 10, is 0.2 meters per second. So from the graph, I could find my speed, and that number is called the slope of a graph, which is basically how steep the graph is. Now let's try another one. I'm going to do this one in blue. If I went, let's say, all the way up here from x equals 0 to x equals 1, 2, 3, 4, 5, 6, 7 to x equals 7, and it took me the same number of seconds, 10 seconds. In that case, my delta x is I went from 0 to 7, which is a total distance or displacement of 7, and I went from 0 to 10 seconds. So my delta t equals 10 seconds. Now if I plug that into my velocity equation, I get v velocity equals delta x, which is 7, over delta t, which is 10, which equals 0.7 meters per second. So the second one, my blue line, is faster than my black line. And that makes sense because the blue line is steeper than the black one. So faster equals steeper, and slower equals flatter. Okay, a steeper line goes faster than a slower one. So the next little thing we have to talk about is what speeding up looks like on a position time graph. And this really isn't that hard, but we're going to talk a little bit about it using slope, which we just discussed. So if I have a car moving at a constant velocity, its line is straight. This is time, this is position. Its line is straight because it's going at a constant speed. And the speed is the slope, how steep it is. It's got a constant steepness there. But if I wanted to get faster, I'd have to get steeper and steeper. I'm going to do this with a green line. So I'd start off at some speed, and then I'd have to get a little bit steeper every second, because a little bit steeper is a little bit faster. And if you put all those lines together, you get a curve. So speeding up looks like curving up. However, slowing down means you start off at some speed and it gets flatter and flatter, which looks like a curve down. So on a position time graph, curving means speeding up or slowing down. If the curve gets steeper, it's speeding up, and if the curve gets flatter, it's slowing down. So let's look at a couple of examples on this. Let's look at the first one. I know the picture is really bad quality, but it'll be okay. So on this one, we start off pretty shallow. But as we go, we get steeper. And going shallow, which is a slow speed, to a steeper line, which is a fast speed, is speeding up. So this graph shows something that's speeding up. Now let's look at this other one. We start off shallow. As we go, what are we doing? We're still getting steeper. It's just going downhill. So this means we're getting faster, but in the negative direction, which isn't something you have to worry about. But it's still getting faster because it goes from a flat line to a steep line. Now let's look at these two. This one starts off really steep, and as we go along through time, it gets flatter. That one is slowing down. Slowing down. Now we look at the other one. It starts off pretty steep and ends up being pretty flat. Steep to flat still means slowing down. So now before we go, we're going to do a little bit of practice. You have a 3-page practice in your Google assignments, which you'll finish today and tomorrow. But I'm going to do the first page with you so you know how to do it. Here's what the practice looks like. It's called Uniform Motion Worksheet 5A. And we're going to do the first bit together because it's got a few things that we didn't really talk about so far in the video. So to start with, we'll read the question. It says, Robin, roller skating down a marked sidewalk, was observed to be the following positions at the times listed below. On the axes above, plot a position versus time graph for the skater. So we're going to plot these points. Now, if you don't know how to plot points, that's okay. We'll figure it out together. But we've got a table here that tells us all of our data. And what this stuff means is that at this time, in the first column, Robin is at this position that's right there. So let's plot those points. At time 0, Robin is at x equals 10. So we've got to plot that. But before we can plot it, we have to know what all these lines mean on our graph. We've got to make sure they fit correctly. So let's look at our times. We go from 0 to 10 seconds. And we're going to see if there's enough lines for there to be 1 second per line. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there are. So I'm going to start off with 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds for Robin. And then I'm going to look at the meters, the distances. She gets all the way up to 30 meters. I don't think there's 30 lines there. I'm going to count and see how many there are. There's 1, 2, 3, 4, 5, 6, 7. All right, so if we count by 5s, we can make it past 30. So I'm going to count by 5. 5, 10, 15, 20, 25, 30, 35. All right, and now that we have our scale done, we can graph these points. The first one is time 0, so we're going to go to 0 on the time axis, and all the way up to 10 on x, which is right there. So we're at time 0 and position 10. The next point is at 1 second. Robin's gone 12. So I'm going to go over to time 1 and up to 12 meters. Now 12 is in the middle of two lines, so you got to estimate a little bit, but that's okay. Next one is 2:14. So go over to time equals 2, x equals 14. The one after that is 5:20. So I go all the way over to time 5, all the way up to position 20, put a dot. And we got the next one is 8:26. We go over to 8, up to about 26, put a dot. And the last one is 10, time equals 10, over to 30. So now we've plotted the whole thing. And we're going to answer the next question. It says, how far from Robin's starting point was she at 6 seconds? So we're going to go look at 6 seconds. Now what you may notice about 6 seconds is that there's no dot there at all. We don't know what where she is at 6 seconds. To figure that out, we have to connect the dots. So I'm going to take my red pen and I'm going to connect all of these dots together. And that looks like a pretty straight line, which we know means constant speed. So at time equals 6, if I follow time equals 6 up, I find the line, and wherever that point is where she's at. So at 6 seconds, we're going to know she's at about 22 meters. So at time equals 6, she's at 22 meters. How do we know? Graphed the line. We graphed the line to find it. And now we can move on to the next question. It says, write a mathematical model to describe the curve in A. Now, for those of you that are in algebra, we basically find the equation of the line using point-slope form, which looks like y equals mx plus b in math. But since most of the IPC kids aren't in algebra at this time, we're just going to skip through this question, and it'll be fine. And we're going to go on down to question D. Was his speed constant over the entire interval? How do you know? Good question. Let's go look at the graph. So what we're looking at was the speed, and the speed is the same as the steepness of the line. And that looks pretty much the same throughout. It stays about the same steepness. So over on this question, we're going to put yes, same steepness, which is also called slope. All right, so I think that is sufficient for you to be able to finish the rest of that practice on your own. Please let me know if you have any questions.